So today we're happy to have Gabriel presenting in a special Berkeley seminar. So he's been visiting here at Tobos a bit this week and last week and working with Kevin and me on how to present models of double theories, building on his work with some others on presenting profunctors. But today he's going to tell you about something totally different, his work to do, I think, with category theory and its relation with model theory, as I understand it. So looking forward to the talk. Thanks.
Great. Thank you, Evan. Hi, everyone. I'm very happy to be here and grateful for the invitation to give a talk at the Tobos Institute seminar. So the topic here is arboreal coreflections. And so the first thing I should say probably is that the context of this talk and this topic is a research program called comonadic semantics, which is trying to bring categorical tools into a very specific kind of model theory, which is finite model theory and also what's called research-sensitive model theory. These are very different in flavor from traditional model theory, which usually studies more infinitary kinds of structures. I won't have time to get too much in detail about what this is. I will try to give some context so that things make sense. But this is a very rich area with connections both to traditional model theory and to computational complexity and database theory. So it's sitting in that kind of spot. But in the context of this research program, there is a kind of script that happens that one can run when we start with some logic that is among the ones that are studied in this area of logic. One starts with some logic, then one comes up with a game, or rather looks into the literature for some game that captures equivalence of models for that logic. And then one encodes that game as a comonad, and then one looks at the category of coalgebras of the comonad, the Eilenberg-Moore category. And that category turns out to have a lot of good properties that are capturing what's going on with the logic. And arboreal categories are an attempt at axiomatizing all those good things that these categories of coalgebras have. So this is the usual way in which it goes, and this script has been run for many different logics. But we want more examples of arboreal categories, and we also would like to be able to produce them without games, without having to figure out what figuring out a game is kind of an art, it's a very specific way of constructing this categorical object. We would like to be able to have more flexible ways of building them. So in this talk, the idea is that for some cases, some very particular kinds of arboreal categories, we will be able to obtain them by working in an ambient category, looking at a full subcategory, and closing it under colimits in some way. And if we chose this full subcategory P correctly, then we will get an arboreal category. That's the idea. And so, yeah.
Is it possible you could give a very quick example of the usual excerpt, like a logic comonad?
I will. This is just like, yeah, so like the logic that I'm going to be talking about is model logic, basic model logic. The game is the so-called spoiler duplicator game that I will try to explain kind of quickly. Then we do get a comonad that I'm not going to be talking about explicitly, but I will talk about the adjunction of the comonad. So this is very, very broad, just to give you the idea that we're reversing the script, and that's kind of the point of this work. And so if you want all of that in a statement, it would be, to take away, it would be arboreal coreflections in a category of pointed relational structures can be classified by good classes of structures, which would be these choices of P. So I have to explain these three things so that the phrase makes sense. But yeah, so that's what I'm going to do. So here's the outline, some context. I need to define arboreal categories carefully. We'll have some steps to get there, which is the main concept. And then introduce arboreal coreflections and some of the stuff that I've been doing with them. And I'll end with some applications to obtain new examples of arboreal categories, and then just some discussion of future work. So as for context, I'll say some words about model theory and this kind of model theory in particular. This is very different from other areas of logic. Here we treat a logic as some way of specifying what properties of some objects are expressible. So we treat our language as some inductively defined class of properties, basically, like the formulas are just properties. And we need to know properties of what. So those are going to be the relational structures in our case, which I'm going to define in the next slide, but you could think graphs or posets. And we are thinking of the logic as inducing an equivalence class, which is called logical indistinguishability, which is relating two of these objects if they satisfy the same properties, the same expressible properties, the same formulas. Now, it's important, of course, to know when some property is not expressible using some logic, which is usually harder than just exhibiting a formula that shows that something is expressible. And in traditional model theory, you could use the compactness theorem. That's a very good option. In finite model theory, you can't use the compactness theorem. It's just not true when you restrict to finite structures. So comparison games are the most important, the most used technique. And I'll try to give an example quickly, but it won't be necessary to understand the comparison games themselves for what I'm doing later. So now to be a bit more precise, I'm going to say some very standard material on relational structures, just so that everyone knows what they are. We start with some signature, which is just a set of relational symbols, each of which has a specified arity. A relational structure is on the signature is just a set, a carrier set, together with an interpretation of the right arity for each relation symbol. So there's going to be relations of different arities on a carrier set. A homomorphism of relational structures is just a function between carrier sets that preserves the relations in the obvious way. And we'll just use this notation for the category of sigma structures and homomorphisms. And also I'll be using a lot the category of pointed sigma structures where the homomorphisms are required to preserve the base points. So as an example, the example that I will be using most, we can take our signature to be just one binary relation E, which we call the accessibility relation, the graph relation. So that's going to give us a graph structure on our set. And then some collection of unary symbols, which we think of as propositional variables or labels for the vertices of our graph. So an example would be something like this. So we have a graph, we have a base point, and then we have some labels on the vertices, right? And in the context of logic, these are called Kripke structures. Is that clear? Okay, so the fundamental logic for predicating on these kinds of structures is basic model logic. So I'll just briefly introduce, the basic things about it. So it has this grammar. So a formula can be just a propositional variable, can be a conjunction of formulas, can be a negation of formulas, or it can be these formulae obtained by applying a diamond operator, traditionally called the necessity operator, even though that's not an intuition that we'll be using. And, well, you interpret it in the traditional way. You have to pick a structure to say whether a formula is true or false in that structure, and you also have to pick a point in the structure. So if your formula is just a propositional variable P, it's true in point A, if and only if A isn't the interpretation of P, which is just a subset. And the actually interesting or like the relevant clause for the semantics of this logic is the diamond clause, which says that the formula diamond of psi is true in A if there is a successor A prime of A such that psi is true in A prime.
What's the successor?
Successor is just some A prime such that A prime is in the interpretation of the graph relation. So it's just a successor in the graph. Like here, the unique successor of A is this one labeled with P. And P, this vertex labeled with P has two successors. So just following the edge relation.
So single edge on path.
Yeah.
I thought your next slide was more general, not just about this one example.
Yeah, no, it is about this example with this signature. So you always have, for Kripke structures, you always have a binary relation that gives you a graph. And then, yeah. So this is an example of fixing this signature, and that gives you this category of Kripke structures, which is just pointed relational structures with this fixed signature.
So
Yep.
when I'm thinking of like model logic with respect to these graph structures and inscription, I'm thinking like the nodes represent possible wells and the edges represent possible transitions between different wells or something. And then you're saying that this like diamond operator, in that well, there's some it is necessary that.
Sorry, I said necessity. I meant possibility.
Possible.
I meant possibility. Yeah,
Okay.
I'm sorry.
And then, but you were saying also that that sort of intuition isn't. Does it not hold, or is it not useful?
It's not how I'm used to thinking about it, because it's possibility in the sense that if you think of the edge relation as saying what accessible worlds there are, but for me it's just successor. It's more natural to think of it as some state transition system or something where the diamond is not so much possibility as there is a successor state where this holds. But yeah, you can think about possibility too. Sorry, I mixed the two. Okay, so yeah, so here's just an example of how you would read a formula like this and convince yourself that it is true in this pointed structure. So I would read this as saying, start at A, move once, reach somewhere where P should hold. So we can do that by doing this, and then move once more from where you left, and you should arrive somewhere where Q does not hold. So if we move here, we can achieve that. So that's just in other words, because we have this path here, the formula is true in this particular example. So hopefully that's enough to get a feeling of what basic model logic is. And now, as I was saying, we're interested in when some property is not expressible by some logic. So as an example, BML, basic model logic, cannot express the existence of a triangle like that anywhere. And to prove this is just to give you a taste of what it means to prove this with a game. You consider two structures, one of which has a triangle, the other one doesn't. And you play the spoiler duplicator game, or analyze the spoiler duplicator game between these two games. Between these two structures. So the idea is each player, there's two players, spoiler and duplicator, and there's two pebbles placed that begin placed in the base points of the two structures. So spoiler is going to pick one of the two pebbles and move it along one edge. Duplicator has to pick the other pebble and move it along some other edge in the other structure, and duplicator should match what the spoiler did in the appropriate sense. So for instance, if spoiler moved to somewhere labeled with P, then duplicator has also to move their pebble to vertex labeled with P. And so in this case, it's very easy to see that the duplicator will always win, or rather always has a winning strategy, no matter what the spoiler does. And because of a theorem, which in this case is the Hennessy-Milner theorem, that is the same as saying that the two structures satisfy the same formulas from basic model logic. So that means that the triangle, it can't be expressible using a formula, because they're equivalent, but one of them satisfies it and the other doesn't. So
what does it mean to win?
it means, so duplicator wins the game if they can match every possible move by spoiler and they never lose. So it's like they don't lose. That's what it means for the duplicator to win. And the spoiler wins if they can do so. For instance, if the spoiler moves this, starts it with the pebble here, moves it to the top, and the duplicator answers by moving the other one downwards, that would be a mistake. Because in the next step, the spoiler can move again, but the duplicator cannot move at all, so the duplicator loses. So that would be the wrong strategy. But there is a right strategy, which is pick the other one. Yeah.
Couldn't one resolve this by requiring that every label is unique? Because then in the last move,
well, it's not just about the labels. Like in this case, there are no labels so for simplicity, I didn't put any labels on the vertices here. So even just the graph structure can lead you to having things that are not equivalent. but the labels are also important.
If every label is unique, then one could express something like commutativity by saying you have to end up at the same unique label.
Okay, well that I think that's interesting, but we should talk about that later. But I think you can't do that way either. But yeah, so yeah, this is not really. This is just to give you a flavor of what this whole topic that we're trying to apply category theory to is. In this way, there are many games that have some flavor like this. We can encode them as comonads on the category of all the structures that we're looking at. And the idea is when you apply your comonad, the endofunctor, to some structure, you get another structure. And the set, the carrier set, is the all possible place in that structure, something like that. Well, as I was saying before, in all the examples, the category of coalgebras turns out to satisfy these axioms that I'm going to tell you about, the arboreal axioms. And these recover all the interesting behavior of this comonad. So what I want to argue is that the more conceptual or axiomatic viewpoint on this whole thing is kind of forget about the comonad as the object of interest in itself and look at the adjunctions, where E is your category of interest, your category of relational structures, and A is some arboreal category. That will be the change in perspective, the perspective that I will be adopting. And in the case of basic model logic, we do have a model comonad. I'm not going to, I mean, you can read what it does from looking at the adjunction. The adjunction is a coreflective adjunction. So the left adjoint is the inclusion of a full subcategory of Kripke structures, which are the Kripke trees, which are basically graphs where, which are trees, directed trees, and the root is the base point, right? And the coreflector, what it does is this operation called the unraveling of a graph, which basically takes the graph to the closest tree. So you start at your base point, and you move along the edges, and every time you reach a vertex, even if you had reached it before, you add a new copy so that you don't have loops. And to finish the story of how this captures some logic, basically there is this notion of a special kind of morphism in arboreal categories that I won't define, which are called open pathways embeddings. And then the equivalence with respect to some to the logic that you started with is captured by the existence of a span between the coreflections of your two structures, where the legs of the span are of this special kind. But this is just more stuff that I don't have time to talk about. So hopefully that gives some introduction to the whole topic, which is pretty vast, I think. But so now we want to talk about what these arboreal categories are. And the intuition for them is that to build a tree, you take a bunch of branches and you glue them along initial segments, which could be something like this, or better, something like this. So if you look at a tree as a directed graph, and you look at all the branches of that tree which contain the root, I'm always requiring that they contain the base point, which has to be the root of each of these subgraphs. I can look at also at the incidence relations between these branches, or like linear subtrees, and then consider this as a diagram and take the co-limit of this diagram, and I recover the original tree. So that's part of the axioms. That's in my opinion, the central axiom. And so we need to define what these branches should be. These are objects or sub-objects that are intuitively linear, but we want to be axiomatic, so we have to come up with a way of defining what those are. And we want to call these objects paths. Okay, we'll call them paths. So if the one obvious idea, or like one intuitive idea, would be that a path is something such that everything inside of it is ordered linearly. So like the sub-objects are linearly ordered. And that's the idea that we want to use. But there is a little problem, which is that, for instance, we would like this to be a path because it looks linear, but the sub-object poset is not linear for a possibly silly reason, depending on how you think about it, which is that these subobjects are not just the strong subobjects, which are the induced substructures, right? An induced substructure is just pick a subset, and then that defines your substructure by adding all the relations that there were originally. But we could have things like this, where this subobject doesn't have the label here. So there is no map from here to here making this commute. And so this subobject poset is not linear. So we need to restrict to strong subobjects, or because this is all done in more generality, we consider M subobjects with respect to some factorization system. But in our examples, it will be the strong monomorphisms that we're looking at as or strong subobjects. So here's a slide with the definition of the kind of factorization system that we're looking at. It's in particular an orthogonal factorization system. This is not really something that I want you to get from the talk, and also it's quite likely that many of you know about this kind of objects. But basically, we require that there is this pair of classes of morphisms in our category. Q, I'll be calling the quotients, and the morphisms in M, I'll be calling the embeddings. And we require that every morphism in the category factors as a quotient followed by an embedding, and I'm using this special arrow notation for that, for quotients and embeddings. And then, well, we have all these other axioms. Q and M contain isomorphisms and are closed under composition. Because it's a proper factorization system, we require that all quotients are epimorphisms, all embeddings are monomorphisms. And we have this pullback condition that the pullback of a quotient along an embedding exists and is also a quotient. And this is what we're calling a proper stable factorization system, which I'm writing as PSFS because I'm going to write it a lot. But this is an interesting part of the axioms, but I will be concentrating more on other parts of the axioms. And just so you know, and you can be safe, that in all the examples, the quotients are just the epimorphisms, and the embeddings are just the relational embeddings, so the inclusions of induced substructures that I was referring to before. Right, so with that in place, we can define a path. A path in a category with a proper stable factorization system is an object such that its poset of M subobjects, which I'm writing like that. I don't know if I'm using that notation. Anyway, well, we require it to be a finite linear order. We also require that paths are like finite length, or however you want to think about it. And we use that notation sub P for the full subcategory of paths in a category. And so in our example, in our running example, the full subcategory of the Kripke trees inherits the factorization system from the ambient category. So there is an ambient, the category of sigma structures in general does have this factorization system, which is proper and stable. And the good news is we have a subcategory which inherits by restriction this factorization system. And then with that choice, which is just the strong monomorphisms, the paths are what we wanted them to be. These are the rooted trees with a single branch. One way of saying it. Yeah.
Just be sure I'm not missing. In a lot of categories, the things that feel like paths, this definition probably doesn't pick them out, right? Like if I'm in the category of categories, I think a path in the intuitive sense is not a path.
Yeah, that is right. So here, the reason. So if we looked at this in the entire category of Kripke structures, so including others that are not necessarily trees, this is not a path, because you could have, for instance, the strong subobject consisting of just the first and the third vertex. That's like a discrete graph. It's a strong subobject, and it's like you have. Yeah, and it's not going to be linearly ordered. So it's a very specific definition of path. And in this case, it's working because these are pointed structures, and we require that everything, that the structures, well, are like initial segments of the other structure starting at that. There are other ways of obtaining path objects in other kinds of arboreal categories, but this is the example that I'm giving now. And so, arboreal categories, what are they? So, first of all, we have a category. We need that the subobject posets are sets, but just a technicality. We require that the category is equipped with a proper stable factorization system, and then there's three conditions. The first condition is one that, well, it's kind of new. There was a previous version of this which turned out to be incorrect for a very subtle reason. So this is a new version. This might be the first talk in which anyone talks about the new version because this is relatively new. But so the first axiom is paths are tree connected. What that means is we have to look at something called tree-shaped diagrams of paths. So these are going to be diagrams where the index category is a poset, which is a tree order, right? And then the image of the diagram consists of paths and embeddings between them. And so we're going to require that each of these diagrams has a colimit, and every map from a path into one such colimit should factor through some of the elements some of the objects in the diagram. And well, in fact, there has to be at least object in the diagram according to the tree order, such that this map factors through the corresponding object. So I'm just going to give like a kind of a picture and hope that it makes sense to you. Here we have some tree-shaped diagram of paths and embeddings, which gives this little tree as a colimit. And then if we map any other tree into this, or rather, sorry, any path, so any linear tree, any tree with a single branch here, it should kind of intuitively factor through some of the branches. So that means that we're going to be able to factor it through some of the objects in the diagram. Then, yeah, there's more to say, but I'll leave it there. The second condition for arboreal categories is a version of the 2 out of 3 property for quotient. So it says that if we have two maps, composable maps between paths, and any two of the two maps or their composite are quotients, then the third one is a quotient too. And the third one that I was referring to before is called path generation in the literature. I also like to say that the full subcategory of paths P is M dense in A. And what it says is that every object in our category A, in our arboreal category, has to be a canonical colimit of path embeddings. So what that means is that we look at this diagram, which is indexed by all embeddings from a path into our object. We take just the domain of those embeddings, and we take the colimit of that. Or rather, yeah, that should recover the original object. And we should be able to take the canonical cone as our colimit cone. So this is true in the example that I've been talking about. And what I mean by the canonical cone is simply that the colimit cone should be, for instance, if this is the domain of some embedding alpha, then this leg of the colimit here is alpha. That's the canonical colimit. And it turns out that this Kripke tree satisfies all these axioms. So it is an arboreal category with the inherited proper factorization system from the category of all Kripke structures.
Is there any claim that this canonical colimit of paths is tree-shaped, or is this a whole other set?
It is tree-shaped. That's a consequence. It is tree-shaped. But that's a good point. So this is a canonical tree-shaped diagram. But when you are looking at this, you allow non-canonical ones. So for instance, this is not the canonical diagram for this because it's lacking some, I don't know, it's lacking like only this upper diagonal edge here. That should be one of the objects in the diagram. So this is not a canonical tree-shaped diagram. Yeah.
Usually that 2 out of 3 property, you don't expect that to be empty. What is it about this?
So this is really just capturing. So in the case in which these are like surjective maps of trees, which we're looking at, this just says that if we have that the composite is an epi, well, the G is going to be an epi too, but we also require that F is an epi. And what that means is that essentially these maps of trees cannot collapse edges. They preserve the height. So I mean, that's what's going on here. So like if you have imagine that you had loops so that you could collapse edges. So you could do something like where you could just do something like this. So this would be an example. So if these are the kinds of objects that we're looking at, or like the kinds of graphs, we could do this. But then we have a surjection where the first map is not a surjection. And that happens because we could like squash some of the edges. And in this notion of tree, you can't do that. So, and indeed, I have an example where everything holds except for this one, because it's precisely like loop trees where you have things like this. So that wouldn't be an arboreal category, but it's also possibly interesting to look at. Yeah, so I'm getting to the actual new thing, which is arboreal coreflections. Now we know what an arboreal category is. I've also mentioned that they usually come with adjunctions, so we care about the adjunctions they come with. And in the case of BML, we saw that the adjunction was coreflective, right? So the left adjoint is an inclusion, or more invariantly, it's full unfaithful. So this is equivalent to saying that the modal comonad that arises from this adjunction is idempotent. And we know that if a game comonad, right, like a comonad capturing some logic is idempotent, that is correlated with some properties of the logic. So it means that the logic has this property, bisimilar companion, which says that every structure is logically indistinguishable from the one that you get by applying the comonad. In the case of modal logic, this is a famous property called the tree model property. And this correlates with low expressive power and good computational tractability in terms of like finite model theory stuff. So this would be like the lower end of the whole spectrum of logics. And it makes sense to concentrate on those if that simplifies things. So the question is, can we study this kind of this situation by reworking the axioms and like simplifying them, maybe? So that's the point. So for that, the first definition is what I mean by arboreal coreflection. I just mean, well, arboreal coreflection in an ambient category E. It's just a coreflective adjunction, sort of coreflected subcategory of E. So that means the left adjoint is full and faithful. But also, I require that A inherits the factorization system from the ambient, so that I only have to fix the factorization system once, and then I look at how that's inherited in different subcategories. And then, of course, I'm requiring by definition that with that inherited factorization system, this subcategory is arboreal. Now, if you want to generalize, you should have at least 2 examples. So I should quickly talk a little bit about this other example of an arboreal coreflection that I've studied with my advisor, Santiago Figueira, which is just a small variation, but interesting variation on basic model logic, where the atoms are not just unary variables that can be unary prepositional variables. They can be relations of any arity. So now you have a graph which is sprinkled with tuples belonging to relations of any arity. I think, in the interest of time, I'm not going to like say much about this because I want to get to the other stuff. But yeah, so this also gives an arboreal coreflection in a category of pointed sigma structures. And it's very similar. But the thing here is when you look at the paths, or rather the whole arboreal category that you get, you only have consecutive tuples. So if there were any non-consecutive tuples, like this one relating these 2 vertices, when you do the coreflection, you lose that information. So you only get tuples that are consecutive along the edges. But I wanted to give just another example because I want to point at a commonality, which is that, in a sense, these very simple structures are reifying very simple formulas. And what I mean by that is that maps out of each of these paths correspond with, like, or rather witness that a certain formula, which is on the right, holds in the codomain of those maps. So until now, there hasn't been any connection whatsoever between all of this and the syntax. So we would like to think of that, right? Like to see if there's any way in which we can read the syntax from the semantics in this way. So this is one of the first intuition that I want to give for the next step, which is that a choice of shapes for these paths should dictate some meaning for the diamond operator. I didn't say what the diamond operator is in the case of this other logic that I showed you very briefly, called PPML. But basically, every time you add a diamond to your formula, it's like exploring further in some kind of structure. So it makes sense that what you choose as paths, as possible paths, would be telling you about what the diamond operator does. And then on the other hand, the third axiom of arboreal categories says that the whole arboreal category is generated by the paths. So that means that a correct choice for this category of shapes, this P, a correct ansatz, should give you the whole arboreal category by just taking colimits. So that's motivating the definition of a seed for an arboreal category. So first of all, a pre-seed is just an essentially small full subcategory in E. And to give conditions for that to be a seed, I'm going to look at its M-dense closure. So what I mean by that is simply the full subcategory where I add every object such that it's the canonical colimit of this diagram, which is just like what I showed you before, except that here P is just an arbitrary choice of pre-seed. It's not paths anywhere yet, but it's what I would like to be paths. So I pick my P, and I can consider all the objects that are canonical colimits of embeddings from an object of P into my object. Does that make sense?
QR will always contain P here.
Yes.
Right? It gets the identities.
Yeah, exactly. And now, well, when is this a seed? Well, there are some conditions that can be expressed just in terms of P. So all the objects of P should be tree connected, and they should satisfy these 2 of 3 property. And then I have to look at this closure and require that it inherits the factorization system that is coreflective, and that the paths in the closure are the objects I started with. That's also something that I would need to ask. And in this way, this is set up so that arboreal coreflections are in bijective correspondence with seeds. So this is just a reformulation so that we can just study seeds, and that will give us everything we can know about arboreal coreflections. And so I wanted to give two things that I've been, or 2 things that I've managed to prove until now. The first one concerns this last thing, which might seem harder than it actually is, because we have this lemma that the paths in the closure are precisely the objects of P, if and only if the objects of P are paths in themselves, which is the intuitive thing that you would ask from the full subcategory P without looking at anything else. So what that means is that for every object P in mathcal P, the poset of M subobjects with domain also in P is a finite chain. So it's like all the objects of P are paths when we look at P as a category in itself. And just to give a taste of how this is like pretty much like order theoretical in a sense. So I want to show you how, if we assume the right-hand side, this thing I said about like the subobject of, the poset of M subobjects of P with domains also in mathcal P, then we can show that the whole poset of M sub-objects, where the domains could be in the closure, could be other things, is also totally ordered. So by contrapositive, we assume that there are two M sub-objects of P, which might be co-limits, which are not comparable. So there is no arrow like this making the triangle commute. But now we remember that these are co-limits. These are canonical co-limits of objects in P, in mathcal P. So we can look at each embedding from an object in P. So this Q1, Q2 would be objects in mathcal P. Would be potential paths, maybe I should call them. And now there has to be, for instance, if we look at x1, there has to be some n1 such that there is no arrow making this square commute. And why is that? Well, because if every choice of n1 made this square commute, we could show that all of this maps from x1. Sorry. Yeah, we could show that all of these maps, diagonal maps, assemble into a map from the co-limit, right? So we would be creating this arrow that we said doesn't exist. So for some choice of n1, there has to be, so for some choice of n1, there is no arrow in this diagonal direction making the triangle, the square commute. And analogously, for some choice of n2, there is no diagonal arrow in this direction making this square commute. And from there, we have found two, if we look at the composites, these are embeddings into P from an object in mathcal P, which are not comparable with each other. So that means that our object P was not a path in mathcal P. Well, hopefully that made some sense, but otherwise it's okay. We can get back to that later. And then to finish, I want to talk about another aspect of this seed axioms, which is the coreflective part. Just saying, oh, by the way, you want your closure, your co-limit closure to be coreflective. That sounds like it might be hard to, or like you just have to come up with the adjunction from nothing. And but that's not true, thankfully. And originally, when I was coming up with this notion of a seed, I wasn't sure which notion of co-limit closure to take, because there's many. The one that I've been talking about is this so-called M-dense closure. We could just look at the dense closure, which is the traditional, maybe more traditional notion, where instead of looking at embeddings into X, I just look at all maps into X from some choice of subcategory. I could just say, well, just add in all the small co-limits of diagrams that factor through your category. That would be another notion, which I'm calling the one-step closure. And then you could do the many-step or iterated closure, which is just the smallest co-complete subcategory. Remember that E is co-complete. So the smallest co-complete category that contains P, that would be another notion. So in a sense, I had to choose between them. But we know that the dense and M-dense are contained in the one-step closure, which is itself contained in the iterated closure. So that's good. And also, under some conditions, dense and M-dense are really the same. So this is the one that I like for what I'm going to show you later. If you know that the one-step closure, which contains both of them, inherits the proper stable factorization system, you do require it to be proper and stable. And you know that the paths in here are precisely the object you started with, then the dense and M-dense closures are the same. So that simplifies things a little bit. But we still have the other three notions. And it turns out that they coincide exactly when the closure is coreflective. So the case in which we're interested in, all these notions coincide. So the following are equivalent. First, that the dense closure is a coreflective subcategory. Second, that the dense closure, the one-step closure, and the iterated closure coincide. And third, that just the first two coincide. That's enough. And notice that this doesn't talk at all about the factorization system, so it's like more general, and I thought it was an interesting thing in itself. And so this is a way in which we can identify, depends on how you think about it, but in a sense you're identifying coreflective subcategories without having to know what the right adjoint is, what the coreflector is. And so to give you some idea of the proof, this is where density comonads come in. So I'm going to be looking mainly at the density comonad of the inclusion functor from P into E. Formally, this is defined as the left Kant extension of the inclusion along itself. And that already gives it a comonad structure with a certain co-multiplication and co-unit. But because we have co-limits, we're in a co-complete category, etc., we can actually use the pointwise formula, which is nicer and makes it clear why this is related to the things that I've been showing you, which is that the endofunctor acts on an object, taking it to the co-limit of its canonical diagram of maps into X from our subcategory P. And so using this, let's first see that coreflective implies that all the closures coincide. So first of all, we know that the dense closure is coreflective in E, so that means that the inclusion I is a left adjoint. And we also know that by definition almost, I haven't said what the definition of being dense is, but it's the same as, like it's like being M dense, but with this notion of maps instead of the embeddings. So it happens for this particular situation where you have a dense functor followed by a left adjoint. The density comonad of your left adjoint doesn't change when you precompose it with a dense functor. It's isomorphic. So that's this first step here. The thing we're interested in is isomorphic as a comonad to the comonad of I. But there's also another very basic fact about density comonads is that if you start with a left adjoint, the density comonad that you get is the comonad that arises from the adjunction. Like you don't get another comonad. If your functor already gave you a comonad, you don't get a new comonad. You get the same one. So that's how we conclude that the density comonad of J is the comonad arising from the coreflection. But because this is a coreflection, that means that the density comonad is idempotent, and that its category of coalgebras can be identified with the domain of the left adjoint, which is the dense subcategory. But now we have this nice result that I found in this paper by Applegate and Tierney from 1969, which is pretty cool. And it specializes to the case that, in this case, to saying that if we have the density comonad of an inclusion being idempotent, then its category of coalgebras is precisely the one-step closure. So that means that the two coincide. And then finally, because this is coreflective, it's closed under colimits. So iterating the closure by colimits will not add any new thing. So that's also why it's equal to the iterated closure. And then, well, the 2 implies 3 is pretty obvious. And so to see that 3 implies 1, we know now that the dense and one-step closures coincide. From the pointwise formula, we know that for any object x, when we apply the density comonad, it's going to end up in the one-step closure because it's a colimit of a small diagram that factors through P. And then we also know that for any object in the dense closure, there is a unique isomorphism between A and dj of A commuting with the colimit cones. What I mean by that is, if by definition, if it's in the dense closure, then it is the canonical colimit of maps into it from P. So these are isomorphic, and it's also there is a canonical isomorphism between them, which when we replace A or we substitute this dj of x, say, becomes this canonical isomorphism, between dj of x and dj of dj of x. And by looking at the universal property that defines the co-multiplication that I haven't showed, we see that this is the component of the co-multiplication at x. And so that means delta, the co-multiplication, is an isomorphism, which is the same as saying that the comonad is idempotent. And that means that the category of coalgebras is the one-step closure, which by assumption is equal to the dense closure. So the dense closure is the category of coalgebras of an idempotent comonad. That means that it's coreflective. It's just another way of saying the same thing. So this is like basic manipulations using the density comonad construction, which I really like. And so the theorem that kind of gets all these things together in a way that is nice for the applications that I have right now, and I think can be improved, is that a preseed is a seed for some arboreal coreflection A, if and only if these 5 things hold. So now the first 3 are just checked on P. Each object must be a path in P, the 2 out of 3 property, and then that every object of P is tree connected. We still require that this is our ansatz for the colimit closure. Like we say, well, the colimit closure looks like it should be these kinds of trees, let's say. So we have to check that that inherits the factorization system, and we can just check that it's sandwiched between the one-step and the dense closure, because the M-dense closure, because the other inclusion is always true. So in this way, we show that A is equal to these 2 things at the same time. And it's actually easier to check that some arbitrary small colimit is in A, and that every object of A is a canonical colimit of a certain kind. So very briefly, I'll just show like 2 examples of things that we can show are arboreal coreflections using this. So first of all, there's another variation we can make on this logic that I briefly talked about before. But the point is, if now instead of looking at the logic and then the game and then figuring out how to encode that in category theory, we can just look at the paths that we got and say, can we vary this choice of P and get something else? So here the choice of P was, well, these are the graphs that are finite chains, and they can be labeled or decorated with tuples from some which are always consecutive. So in this case, if it's a binary relation, the tuples have to be 2 consecutive, like a point and its successor, basically. But we could have not added any restriction at all on these labels, on these tuples. So we could just, instead of that, say, well, these are the linear chains, the finite chains, and you can just decorate them however you want with the relations from your signature, like no restriction at all. And that would have been even more natural in retrospect than what I did. So you do get something which I'm calling PPML plus for the time being. And just from looking at this choice of P and what the obvious trees resulting from it would be, using this theorem that I showed you, you can check more easily than it is an arboreal coreflection. And the coreflective subcategory in this case is the directed trees where the tuples lie in one branch. So there is no tuple connecting, there cannot be any tuple connecting things that are in different branches, which in this case is hard. But yeah. I'm sorry. I'm sorry. I don't have time to get too much into detail here. But this should correspond to another syntax, and that's the interesting part. Like just from looking at the new choice of P, this suggests a syntax where now we have to add these indices to indicate which points along a path we want to look at to check the truth of that formula. And then I just want to mention quickly that this lets you define notions of trees where every link in the tree doesn't have to be just one new vertex and some relation. It could be multiple tuples and multiple points. Because so I think this is pointing to a much greater generality than could be seen from the other examples that I showed you. So what if we now say that paths are like this linear chains where every link is one of these triangle shapes? Then it turns out that this is a seed for an arboreal coreflective subcategory, or an arboreal coreflection, where the objects are things like look like this. So you could define them inductively by starting from like in the terms of like skeleton or like height k version trees. So like you take a height k tree, and then to get a k plus 1, you just add more triangles on the leaves. And this is also an arboreal coreflection. And this is probably not something that you could have come up with by thinking from existing logics and the way of thinking about them. And I do think this corresponds pretty simply to another modal logic where the diamond operator expresses the existence of a pattern like this one. But I haven't checked the details. So to finish, I just want to say that I think there's more work to do on these seed axioms. I'm hopeful that there's better things to say about this. For instance, I think that if you look at just this particular factorization system, which is like an image factorization in this case, there might be some ways to simplify what it means for a subcategory to inherit the factorization system. If you have any thoughts on that, I'll be really interested. And I also think there might be some simpler, like easier condition that guarantees the coreflectiveness, so that these different kinds of co-limit closure coincide. And then this example that I just showed you seems like it could be generalized quite a bit. But even though you could think that any pattern would work as a link in the chain, not all of them work, at least not in the obvious way. So something like this, where you have this internal automorphism that switches these two branches, that doesn't work. That fails to satisfy the axioms. And then I think there's the idempotent case, so the case of co-reflective subcategories is really interesting, but it would be even more interesting to study the transition from this into more complex logics and game comonads, basically. And I think, well, I have some ideas how to go about that. And I do think that all the logics that one might obtain this way will look very similar to basic model logic, except that we kind of replace some building blocks. So I would want to make that more formal. But yeah, that's all. Thank you.
We talk about the tree connectedness thing.
Mm-hmm.
Maybe, sorry, if somebody's like so can scroll back to it.
Yeah. Oh, maybe I can.
Isn't that in the yeah. So
Sorry, I actually have to run. Can you close the window?
Yep.
Thanks so much.
bye.
That is awesome.
Are we still recording?
Yeah.
Yeah. So this is like this feels like a very strange, unfamiliar condition from the viewpoint of like accessible category theory. You're saying there's in the second paths are tree connected, right? Okay, I missed that. P has to be a path.
Yeah. So one thing that, from the point of view of like what you're saying, I think this. Let me think. So this axiom guarantees, if I'm not mistaken, that in some sense, I'm not 100% sure, but I was thinking about this like a couple of days ago, that this M-dense closure is the same as what we could call the tree closure, where by tree closure I mean all the co-limits of tree-shaped diagrams of paths and embeddings between them. So there is this argument where you use this factorization along a of a map into a co-limit, like it would be like filtered co-limits, I guess, or like that kind of thing in inaccessible and presentable categories, that lets you conclude that sometimes a non-canonical co-limit forces the canonical cone to be universal too. So it makes the canonical and non-canonical versions of some co-limit to coincide in a sense. And I think that's what's happening here. But I have to say that people haven't really thought that much until now, I think, about this axiom because it's new.
It's not in the original papers.
The original papers will say something much simpler, which is that every map from a path object into a coproduct of paths factors through some of the coproduct legs. And that's actually not true in these kinds of example. Like for basic model logic, that's not true for a very subtle reason, which is that when you take a coproduct, so you could have these two Kripke trees, which are just the root with a label P and Q. But because these are coproducts in a category of pointed objects, like when you do this, you glue the roots, right? So now you have a root which is labeled with both P and Q. And so if you have a map, if you have the identity map here, this is not factor through this coproduct cone because it has to map this point to a point where both P and Q are true and that there's none. So this is what makes that very old version of the axiom fail. But the good news is that this doesn't break things in the sense that there's another condition such that if that condition holds, then this is the same as the new axiom and the old axiom are the same. That covers most cases, and for these cases where you have pointed structures, they're not the same. But this is what you actually used in the proofs. But now it looks more complicated. Like the axiom looks more complicated, and that is interesting for me because it means that maybe I can use it differently in this reworking of the axioms that I'm trying to do.
And you also you use the word connected in the definition, but I feel like it's sort of begging the question because
Yeah.
I've never heard of a tree-shaped co-limit before, right? But if I was starting to wonder about a tree-shaped co-limit, I would say that this looks almost as much like being finitely generated as like being connected, because it's a connected diagram shape, right? So have you thought at all about the relation between this and being finitely generated with respect to the embedding?
I haven't. That's interesting. We could talk about it more. But I will just say that this is just adapting, like the previous axiom, which is factoring through coproducts, is closer to the notion of a connected object, and that's where the connected word is coming from.
Yeah. This seems almost more like kind of a compactness kind of thing.
Yeah. Yeah, it's something like that. Yeah. Oh, yeah, Evan.
I'm just trying to understand the big picture. So at the end, you showed some example where your paths were actually like built out of triangles and stuff. You asked like, well, is there a modal logic that would correspond to this? Now I'm wondering what that even means. Is the idea that like for each arboreal category could be the semantics for some variant of modal logic where you might actually change the connectives or the rules of inference, or what does that mean to have a modal logic that corresponds to that?
That is a great question. Like the one that I would like to answer, like making more of this more precise. But it's really like the correspondence between an arboreal category and a logic is not formal.
Yeah.
So there's no definition. I guess there might be some attempts, but there's no universally accepted definition of what a modal logic is either. So it's pretty imprecise. But what I think is that at least for things like, at least for for arboreal coreflections that you obtain by these two moves that I mentioned. So there's two moves that correspond to these two examples. One move is changing what the allowed decorations are on some underlying graph structure, like whether you are allowed to decorate in all possible ways, or with, for instance, tuples of any arity, or just unary tuples, or that kind of choice. That leads you from basic model logic to these other versions of that I've been looking at. And then the other would be changing what you take to be a basic step in these chains. And then at least I think for these two choices, like you should be able to always get a logic which has the same grammar, or except for the modal operator part, which could be different. Yeah.
Yeah.
With maybe more bold to ask this, since you said that there wasn't like a firm consensus on what modal logic was, but on this slide, and you can feel free to dismiss this if it's nonsense, but like, what is stopping you from considering like simplicial? This looks like a simplicial set type thing, or like, why does it have to be this like triangles?
Do you know of a relational? I mean, I guess you could encode. I mean, I'm not answering what you think you're answering. I'm just thinking out loud. But I mean, like, you could encode simplicial sets in a relational way, I guess. So, do you want to say something about it?
Well, no, I have a question that
Oh,
I
okay.
think is somewhat related to that. So, are you?
Yeah, no.
Okay, cool.
Maybe you can try to answer both.
So sorry if maybe you already said this and I missed it because I wasn't here for
Yeah,
a bit.
sure.
But so you mentioned toward the end that like some shapes don't work, like
Yeah.
a square doesn't work but a triangle does, and you mentioned that's because of like having non-trivial automorphisms.
Yeah.
Is that a sufficient condition for that to work, or is it more complicated than that?
So I think for now, the only, like, this is all work in progress, like recent, very recent. But for now, what I can say is that if your little pattern graph, so if it's rigid, but rather maybe not even rigid, if it has no non-trivial endomorphisms, then it should work.
Okay.
But the reason why something like this will fail, well, basically, it has to do with the fact that you can take a co-limit of, like a co-equalizer of, so there's two maps that collapse the two branches, like to the top or to the bottom. If I take the co-equalizer of those two, I get just one branch. And that is a valid co-limit that I can take just by looking at maps between these things. So I would have to add that to my P, to my category. But if I add that, then these are not paths anymore because the posets are not linearly ordered anymore. So, but this, so I hope that this is related to something that people care about in finite model theory, which is when a structure is Geifman connected, which means that every pair of points belongs to some common tuple in some relation. Because it is true that in this case, like this is a clique, like a Geifman clique, like all points are related to all the others in this graph, and this is not. And I think after like working a bit more in this case, I would like to see if there's a way to move towards a more interesting logic, which is called the guarded fragment of first order logic, where this Geifman cliques play a role. And it's clear that's not going to fall in this, like the comonad is not idempotent, so it's outside of the reach of this, but maybe there's something, like, I'd like to understand what fails exactly when you move in that direction, and I hope that it's related. But yeah, going back to the simplicial sets thing, I don't know.
I was partially asking about this because it reminds me of some stuff that I've had in some conversations over at CMU about like cubical type theory and relating that to simplicial type theory, and it is that kind of thing where like cubes have these like non-trivial automorphisms, and that causes some of the things in
That is
there, not
interesting.
carry over to the simplicial case. So, but maybe that's a conversation we can have.
Yeah.
Once the camera stops rolling, because it's probably
Okay, sure.
a bit of a
That's,
diversion.
that is an interesting coincidence.
Yes. Yeah.
Yes, let's thank our speaker again.
Okay. Thanks.